Hello, Professor De Silva. This is David Sandstrom, Physics 2010 R50, and our topic is how can we harness the heat energy to power the world? We have an introductory slide here, and subtopics are energy, thermodynamics, waste heat, and technology. We'll be talking about energy first and how we use energy globally, what kind of energy we use, and where does energy come from, and then that conversion from energy to thermal energy, how we use it in power plants, smaller scale domestic use, the actual energy conversion process, the byproduct of thermal energy or energy conversion is heat, thermodynamic laws, the use of waste heat, and the technology and our future. The Department of Energy tracks the different kinds of energy we use, and fossil fuel use of oil, coal, cleaner energy uses of hydroelectric, nuclear, biomass, natural gas, renewable energy sources such as wind, water, and then we use solar and geothermal energy. So what do we use energy for? Obviously, anything that we power up. Far right side, we see a pie graph here. 40% of our use in America is on transportation, planes, trains, automobiles. 20% is industry, manufacturing, and then we use about 30% for our domestic lives in our homes, that sort of thing. On the left side here, we've got a chart that breaks down our usage of energy, and what stands out here is a 31% of heat energy and the 12% of water heating. Again, we're using energy to heat different products in our homes. How do we get heat energy? It's from interaction of atoms and molecules, the collisions and the vibrations of those. Heat is a byproduct of all energy transformation. Heat follows the laws of thermodynamics, the first law, second law, third law, and the 0th law. Heat is transferred by 5 different transformations, but we'll talk about 3 here. The first one being radiation. Electromagnetic waves transmitted through empty space to the Earth here. Infrared rays from the sun. Conduction. Anytime there's a hot to cold transfer from object to object, we have a conduction transfer. And then we have the last one is convection, which we use in our atmosphere. Anytime we boil water, those are convection heat transfers. How do we obtain heat energy now? How are we using it? Especially in America and globally. Most obvious is solar energy. We're starting to see a whole lot more solar panels. The price is coming down, even though it is still unfortunately high. And we're starting to see a change to geothermal energy. We don't see it here in America, but it's starting to be more of a global aspect. Iceland is one country that uses geothermal energy quite a bit. By the year 2050, we're going to see a change to nearly 50%. 2050 we'll see a 10% overall change to geothermal energy. There's been studies out there that say 20 miles and below our Earth, we will have all the heat energy we need to actually power the Earth. Of course, the problem is of actually getting access to it. What I found interesting about power plants is that I did not realize until I started doing this topic is that we're using heat to actually power our power plants. So we use fossil fuels like coal, oil, natural gas, nuclear, and we burn these fuels in the furnace. The furnace heats up water in the boiler. The temperature rises, the pressure rises, and then the steam transports itself into a turbine. The turbine is moved and into a low pressure turbine, and it moves a generator, which creates a voltage, and the voltage creates electricity that we use in our homes today. The cooling towers, the steam actually rises to cooling towers, and then it condenses on those cooling towers and is brought back down and is reused. Some of it is piped out toward the top, though. How do we use direct heat today? A much smaller scale. We use it for cooking. We use it for toasters. We use it in our water heaters. We light a fire. use a wood stove. That's how we use it. We use boilers to heat our homes, to heat industry. We use heat to weld, smelting process, and we use blow dryers to dry our clothes, dry our hair. How is energy converted to thermal energy? 6 different aspects here. The first one being mechanical. Anytime we move our muscles, we are creating a mechanical energy, which is transferred to heat. Bouncing a ball will do the same thing. Electric energy. We can touch a light bulb and feel the heat from a light bulb. Chemical energy. There's exothermic reactions that occur when certain chemicals react with other chemicals, which have a heat byproduct. Friction energy. Rubbing our hands together, anytime an object touches another object, there's friction that's actually created between those two surfaces, which also leads to heat. Radiation energy, energy from the sun, is converted to thermal energy. And of course, any heat energy to heat energy creates more thermal energy. So what do we do with all this thermal energy? It's the byproduct is heat. All products we use, anything that's powered, any friction that's caused relates to heat. So how can we access this heat? Our vehicles is one avenue we can use. Our engines and our brakes generate a ton of heat, and we can use that heat if we can turn it around and access that heat. It's going to be a great opportunity to power our vehicles. We can use the exhaust from there too. Industry shoots out a lot of heat that's not being used, and it's wasted into rivers, streams, pools, and then piped out to the very top. And then of course we have this heat that we use in our electronic devices that have heat. You can put your hand behind a refrigerator and feel the heat off there. You can put your laptop on your lap and then feel the heat from that. So what makes it possible for us to actually have the opportunity to actually use this thermal energy? And the first law of thermodynamics tells us quite a bit about that. Energy can be neither created nor destroyed. Energy can be transferred or changed from one form to another. And one of the forms it'll go to has to do with the second law of thermodynamics. Waste heat must be produced as a byproduct of this energy transformation. Waste heat has a higher entropy than the original energy source, and the more energy is transformed, the more waste heat that is actually produced. If we convert energy to thermal energy, and there is a 100% thermal efficiency, that means there's a 1-to-1 ratio, then we actually have maximal thermal efficiency. Unfortunately, we can't be at 100%. In fact, we have difficulty getting to 50%, but there is a cycle called the Carnot cycle that allows us the maximum efficiency that we can possibly get. And it's a different processes of expansion and compression, which allows us to get the highest amount of efficiency we can out of that transfer of energy. When we take the difference between the hot temperature and the cold temperature, the greater the difference that we can use and the compression expansion cycles, then we're going to get the greatest amount of efficiency out of that engine that we possibly get. Unfortunately, it's an idealistic cycle, and it's not been actually been produced. And even if it could be, it's truly not practical due to large heat tolerances, and our materials just could not tolerate the amount of heat that we require to get this efficiency that high, and the isothermal process is way too slow, even for domestic or manufacturing process for it to even use. It's been said that around 60% of our energy is wasted as excess heat, and meaning we only have about 40% of our energy that we're actually capitalizing. 60% is being lost. So if we can capitalize on that greater amount of excess heat being produced, we'll have a higher efficiency. Of course, we have to decrease our friction, heat loss, and conduction of that heat from one area to the other. Unfortunately, all heat can't be transferred to work. Shows a challenge of getting most out of thermal energy. But of course refers back to the inefficiency of energy transfer. One way we've been actually capturing and the inefficiency of that transfer, we actually are deeming that waste heat, that heat that can't be used. But how do we reuse that waste heat? Last couple decades, thermoelectrics has been using that waste heat. Um, Unfortunately, it's very inefficient. It's currently being used on the space shuttle, and the reason is it's got a higher heat differential that's being capitalized on, but it also has very high costs. The materials are very toxic, and it's not something we can use domestically and for our industry right now. But where are we moving? Where are we moving to when it comes to that waste heat? Technology is getting much better. Uh, uh, Materials are better, better conductors. Things are getting smaller. We're now able to capture, instead of the high heat differential, we're now able to capture lower heat differentials. That sweet spot of a lower heat differentials is things like factories and our power plants, exhaust from our automobiles, the energy from the thermal energy from our engines and our brakes. If we can capture that waste heat and turn it back into the energy for the vehicle, that would be tremendous. Our solar cells, we can actually use that waste heat and put it back into the solar cell for more efficiency. And the move to thermal energy may occur from our new technology. So we already have scientists working on these different techniques. And one specific principle that's helping us is the Seebeck effect. And the Seebeck effect allows us to use heat to conduct across conductors and produces a voltage. Then in 2007, Rashba spin effect was combined with the Seebeck effect, and they found a odd occurrence which actually produced more energy, the production of more energy from lower voltage waste heat. And what that does is the lower temperature gradient spins the opposing magnetic charges of a nickel iron alloy and silicone, and they've been able to use it on a much smaller scale at 25 nanometers, and that extra amount of, that smaller amount of size, they've actually been able to produce quite a bit of voltage out of that. So that's one technology advancement that seems to be working. And of course, the materials are getting better too. The move to nanowire-based thermoelectricity, for transfer of waste heat, is actually making quite a bit of progress. So, is there enough energy to heat to power the world? And the answer is yes. We've got many different avenues we use currently right now. Our move away from the fossil fuels to cleaner technology is actually going to make it better for us. Move to more solar, geothermal energy, possibly nuclear. And as we get better at our waste heat utilization on high and low grade heat, especially on the low grade heat side, around 60 to 100 degrees Celsius, we're going to see a whole lot better efficiency when it comes to that. Our technology is growing. Materials are getting better. They're getting smaller. Even on the smaller end, if we were able to use the heat from our computer and apply that back to, say, the screen or the processor, it's quite a bit of heat that we can use to use for energy. So why aren't we using it right now? Cost. It's always about costs. And it isn't until we're going to see the industrial manufacturing sector see a benefit of putting money into R&D and seeing that their costs in the long run are going to drop. That's when we're going to see a change to that field. Right now, there's a lot of scientists studying this, physicists studying this process of this heat transfer and utilization. But of course, we're going to have to increase the efficiency. But as technology is getting better, we're going to see that efficiency getting better. And probably in the next 20 or 30 years, we're going to see quite a bit of change toward cleaner energy and also to the ability of heat energy being used. And then we're going to need to see a global change in just global warming getting better. And we need to see a change from each one of the countries that are willing to actually do better on decreasing our use of fossil fuels. A couple of years ago in Puerto Rico, the unfortunate hurricane rolled through there and destroyed the entire country and their economy. But one great thing happened in the last month. They signed a pact of going to clean energy. And through that clean energy process, they are already investigating on how to use heat in order to power their system. So that's a very good change that's happening. We just need other countries to move that way, especially the United States, who seems to be a leader when it comes to change. So eventually, though, we should be moving to that it's just going to take a little bit longer. That is my conclusion on PowerPoint, but thank you very much.